So in the previous class, we were talking about the structural hazards, and we try to find a solution for the structural hazard that by just separating the hardware resources so that the instructions can continue their execution in the pipeline, like the L1 cache, which is divided into two types, like instruction memory, which will be used in the instruction fetch, and data memory, which will be used in the memory access stage. So let me just show you that when the instructions are fetched, then they use this instruction memory, and when the data is accessed, then they use the instruction data memory. So we call the L1 data cache memory, and the L1 your instruction cache memory, right? So that these two, the same cache is separated into two parts. One is your L1 instruction memory, and another one is L1 data memory. Not two different hardware, only one hardware, but separated it. Okay. Yeah. So the next solution for this is, let the hardware component is same. Let the hardware component same, but if you recall the time that we have seen, one cycle is defined as the edges, the signal edges as upper raising edge and your down edge and your rising edge. This total is known as your one cycle. So in the first cycle, there will be a write operation, and in the second half cycle, there will be a read operation. So this is what we have seen in the previous lecture. So by doing that one, if you see that if there are four instructions, instruction 1, instruction 2, instruction 3, and 4, when this instruction is fetching, when the first instruction starts executing in the pipelining, then the instruction will be in the first phase, that is instruction fetching, and it is utilizing the instruction L1 instruction memory. Then in the second cycle, the instruction 1 goes into the instruction decoding phase. So in the instruction decoding phase, it is going to access the memory. Okay. So as we said, the first half cycle is used for the writing purpose. So that is this half cycle, and second half cycle will be used for your reading purpose. First half is writing, and second half is for reading purpose. So in the second, the half cycle, your instruction 1 is reading the data from the register file. Your register file. Okay. And during the second cycle, your first cycle, that is instruction fetching, is idle, so that will be assigned to your second instruction. So instruction fetching functional units assigned to your instruction 2, where your instruction 1 is utilizing the functional unit of your register file, where the registers will be read out. In the third cycle, your first instruction uses the arithmetic and logic unit, that is in the execution mode, and then the instruction decoding, the functional unit, that is your register file. The register file will be free from your instruction 1, so that will be assigned to your instruction 2. So instruction 2 will be in instruction decoding stage. When instruction 2 moves into instruction decoding stage, your instruction fetching stage functional units are idle, are free, so that will be assigned to your instruction 3. Right? So here you can see this in every stage we are separating that. Instruction 1 is utilizing instruction memory, instruction fetching stage utilizing instruction memory only. Right? In the fourth stage, your instruction 1 entered into your memory access stage. So here the memory which is accessed by your instruction 1 is your data memory. your L1 data memory portion, not instruction memory portion. So there is no clash between the data memory portion. Your second instruction will enter into your execution stage. So second instruction use the arithmetic and logic unit. So where your the third instruction will enter into your instruction decoding. So your third instruction will utilize the register file. Then your first instruction, I mean the fourth instruction will able to get the first stage functional units, that is your program counter. It use the program counter and the instruction memory, not data memory, the L1 cache instruction memory. So here the memory, same memory component is used, but at L1 cache, the first portion, that is instruction memory portion, used by your fourth instruction, and instruction one is utilizing the data memory portion. So there is no clash here, there is no hazard, there is no problem here. Okay, so this at the fifth instruction cycle. Okay, so this is the way we use. But now see, at the fifth instruction cycle, in the fifth instruction cycle, your first instruction is in the write back stage, so that will be used the register file. And at the fifth instruction cycle, your instruction 4 will also access the same component, that is your register file. So then there will be a problem. Same hardware component is accessed. So here, without separating two different hardware portions like your instruction memory and instruction decoding, the register file for reading and writing purpose. At the instruction 4, at the cycle 5, instruction 4 is trying to do the read operation. Read the registers, right? Read the registers. Whereas your instruction 1 is trying to write the instruction, write into your register. So as we said that only one control signal will be active at a time, either write or read will be. So to solve this control structural hazard, the first half cycle is used for your write purpose, and second half cycle, the first half cycle and second half cycle. In the first half cycle, the register will be write. That means your control signal, write control signal given as an input to your register file. So your write port will be enabled. When write port enabled, the value will go and write into the destination register. In the second half cycle, this portion, the read control signal will be given to your register file. So the read ports will be activated, and from those registers, the value will be read from the source registers. So by following the different part of your cycle is another solution for your structural hazard. Am I clear at this point? Good. Yeah, thank you. So then the third way of solution, the third solution is duplicate the resources. Duplicate the resources. So up to now, what we have done, the first solution is you need to, separate the hardware. That is your L1 cache, L1 instruction memory, and your L1, your data memory, when the instruction is accessing the memory unit. Second solution is for your register file. For register file, we use the first half cycle. The first half cycle used for your write purpose, and the second half cycle used for your read purpose, so that the structural hazard because of your memory unit and because of your register file will be solved. A third resource is, if you have more transistors, you can duplicate these resources. You can duplicate means you can use the memory unit at the instruction fetching. You can use a separate memory unit at the instruction fetching stage, one memory unit, and at the memory access stage, you can use another memory unit 1 and memory unit 2. This is another way. Similarly, for at the instruction, at the instruction decoding phase, you can use one register file, your register file 1, and at the write back stage, you can use the register file 2. So that is duplicate the resources, physical resources, so that the instructions can be executed parallelly without waiting for each other. But so the duplicate, this is useful, but what is the problem? By adding these extra components, functional units, that will, that does not increase number of cycles per instruction for the execution, but definitely as the units are increased, their cost will be increased, probably. Okay, and possibly sometimes they increase the cycle time length also. They increase the cycle time also. Number of cycles per instruction will not change, but cycle time may be increased, because every unit has to be accessed and they will be processed, and the signal must be transferred. Signal must be travel from one functional unit to another functional unit. So it may increase the cycle time. So this is the only the disadvantage of that. So the third solution is generally not preferable, but the most of the architect, they used to follow the solution 1 as well as your solution 2. Okay, so these are 3 different solutions for your structural unit. So now let me quickly get into the next control hazard that we called the data hazards. The data hazards. Okay. One is, as we discussed, there are 3 hazards can face in pipeline. One is your structural hazard. Second one is the structural hazard. Second one is your data hazard. And third one is your control hazard. So let us discuss the data hazards. Yeah. So in data hazards, before discussing this, any program that will use the data, so that data may be dependence, and because of that dependency, the hazards will be there. So in any program, suppose if a program is having some set of instructions, like your instruction, suppose J, let me just write, your program is having the instructions like instruction I, instruction J, and the instruction, suppose K. If there are 3 instructions are there in the program, suppose, then determining how one instruction depends on another is critical to determine how much parallelism exists in a program and how that parallelism can be exploited. So in particular, to exploit instruction level parallelism, as we saw in the structural hazard also, we must determine which instructions can be executed in parallel. So if 2 instructions are independent, suppose your instruction I and instruction J or instruction K, if they are independent, then they can execute simultaneously in a pipeline of arbitrary depth without causing any stalls. So assuming that the pipeline has sufficient resources means there is no structural hazard exists. But if two instructions are dependent, like J depends upon your I or K depends upon your J, okay, if any two instructions are depend, then they are not parallel and must be executed in order. First the previous instruction should be executed, then the next instruction should be executed, although they may often be partially overlapped. So the key in both cases is to determine whether an instruction is dependent on another instruction or not. So that we call from there we find the concept of your data dependency. Data dependency. So what is this data dependencies? Actually, there are three different types of dependencies are there. One is the three types of data dependencies. Let me just erase this. Okay. So one dependency is there are three dependencies, data dependencies. One is the true data dependency. So we call this as your the true data dependencies, and your second one is name dependencies. And third one is your what we call control dependencies. So there are three dependencies are there. First one, data dependency, that is true dependency we call that, depends upon the value. Second one is name dependencies, that depends upon the name of your register or memory. A third one is your control dependencies. So that means what? An instruction, suppose J in this case, an instruction J is the data dependent on a preceding instruction I if either J is depending upon the output or the instruction I produces the result, that result will be used by your instruction J, suppose, or instruction J is depend on instruction K, and K instruction is depending upon the result of your instruction I, suppose. Okay, so the second condition, this is the R condition, the second condition, J is data dependent on instruction K, and instruction K is data dependent on instruction I. So it simply states that one instruction is depend on another if there exists a chain of dependencies of the first type between the two instructions. So this dependency chain can be as long as the entire program. And note that a dependency within a single instructions, such as suppose if you have the instruction like add R1, 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 okay? If any instruction which is having in a single instruction, if you have this kind of instruction, is not considered as your dependencies. Dependency considered as one instruction depends upon the other instructions. So that we call the data dependency. Right? So here, this dependency, data dependency, if two instructions are data dependent, they must execute in order, not parallelly, and cannot execute simultaneously or be completely overlapped. So the dependency implies that there would be a chain of one or more data hazards that we'll find from these dependencies. You find either one or more data hazards will be there. So this one or more data hazards between two instructions. So executing the instructions simultaneously will cause a processor with the pipeline interlocks. By executing these instructions simultaneously, suppose, then that will cause the processor with because it will be executed by your CPU, right? So the CPU or processor with your pipeline interlock this pipeline interlocks to detect a hazard and stall the instruction execution, so thereby reducing or eliminating the overlap. So in a processor without interlocks that relies on compiler scheduling, suppose the compiler cannot schedule dependent in instructions in such a way that they completely overlap because the program will not execute correctly. So dependencies are a property of any program. Dependencies are a property of this any program. So whether a given dependence result in an actual hazard being detected, and whether the hazard actually cause a stall, are properties of the pipeline organization. So this difference is critical to understanding how instruction level parallelism can be exploited. So if data dependency conveys three things from this set, what are those? The first one is the possibility of hazards. The possibility of or hazards is one. And second, it conveys that the order in which results must be calculated, right? Which results must be calculated. And the third one is the data dependency conveys the third thing is an upper bound on how much parallelism. It gives the upper bound that how much parallelism can possibly be exploited. So such limits are explode in a proper way. So because a data dependency can limit the amount of instruction level parallelism, we can exploit the few things like a data or a dependency can be overcome in two different ways from this convey. The data dependency can come overcome in two different ways. One is uh, they maintain the dependency but avoiding they must maintain the dependency but avoid the what you call the hazards. Second, the eliminating the hazards. If hazards are there, then eliminate those hazards. Eliminating the hazards. So that is first one is maintain the dependencies. What you call but avoiding the hazard, or if hazards are there means eliminating the hazards without altering a dependence, and such scheduling can be done both by the compiler and by the hardware. So data value may flow between instructions either through registers or through memory. The actual data values of any instruction, suppose we have the instruction like add R1, R2, R3. So the values, the true values that may flow either between your registers, or if you have any register with the memory address, that flow between your register to memory or memory to your register, that is true data value. So that is what saying the data value that flows between your instruction either through register to register, register to memory, or memory to register, or memory to memory. So when data flow occurs through a register, detecting the dependency is straightforward because the register names are fixed in the instruction encoding, right? That is R1, R2, R3. So these are register names. So if data flow is occurring in this register R1, R2, R3, suppose, then identify the detecting this dependency is easy because of the register names which are encoded in the instruction. But although it gets more complicated when branches intervene and correctness concern force a compiler or hardware to be conservative. So dependencies that flow through memory location occurs as load instruction that consumes the data value produced by earlier stored instructions. So that is one. And from there, you will have the name dependencies as we just note name. The second one is your name dependency. So in this name dependencies, this is the second type of your data dependencies and hazard. So a name dependency occurs when two instructions use the same register or memory locations. As we said, if you have the instruction like add R1, R2, and R3, another instruction is suppose subtraction that is using R4, R1, and R5. In that, two instructions, instruction 1 and instruction 2, both are using the same register, or same in the case, same memory location. Right? So this name dependency that occurs because of same register name or same memory location, we call this as your name dependency. But there is no flow of data between the instructions associated with this name R1 and R1 in the add instruction and your subtraction instruction. There is no data flow actually. Okay, the name is same here. That's why we call it as name dependency. So there are two types of name dependencies between an instruction one and your instruction two here. So, and in this is instruction either. So, an anti-dependence between instruction 1 and instruction 2 occurs when instruction 2 writes a register or memory location that instruction 1 reads. So the original ordering must be preserved to ensure that instruction 1 reads the correct value and our instruction 2 reads the correct value. Another one is the second type of second problem comes that an output. So this first one, which is depending, so the subtraction is depends upon the add one. We call this as your anti-dependency. That is based on your names. And the second one, we call that as the output dependency. The output dependency. Dependencies. So this output dependencies occurs when instruction 1 and your instruction 2, they try to write the same register, suppose. Okay, if they try to write in the same register, suppose in R1 and R2, both the instructions try to write in the same instruction, suppose, I mean, same register or memory location, then the ordering between the instructions must be preserved to ensure that the value finally written corresponds to the instruction 2. First, instruction 1 will write, and second, the instruction 2 will write in that. Okay, so this we call the name dependencies. So from this concept, we find there is a data hazards are there that conveys the data possibility of your data hazards. So a hazard that exists, this data hazard exists whenever there is a name or data dependency between two instructions and the two execute with sufficient overlap to change the order of access to the register operand or even memory location involved in the dependency. So because of the dependency, we must preserve what is called program order. Program order. Okay? So that is the order that the instruction would execute in if executed sequentially one at a time as determined by the original source program. The goal of both our software and hardware technique is to exploit parallelism by preserving program adder only where it affects the outcome of the program. So the data hazards, which are informally, which may be classified as one of three type of your dependencies that we call. One is your, read after write, or write after read, or write after write. So in read after read means if you have two instructions, suppose instruction I and your instruction J, suppose, right? So this data hazards, as said, it can be classified in these three types, that depending on the order of read and write access in the instruction, read or write, whether read or write instruction. So by convention, the hazards are named by the ordering in the program that must be preserved by the pipeline. So let us see this, how these three effects, the read after write hazard, or write after read hazard, or write after write hazard. So by just considering these two instruction I and instruction J, with your I is preceding J in the program order, suppose. Your I instruction is preceding J in the program order. So first, let us see this raw, or we call the read after write. So in read after write, what happens here? In read after write, J tries to read source, suppose your J instruction tries to do the read operation, read the source operand before preceding instruction, your I writes, before the first instruction I writes into the register. That means what? If J is depending upon your I instruction, then if before I is writing into the register 1, for example, we have R1, R2, R3, and second one is suppose subtraction, having R4, your R1, and R suppose 5. If subtraction, because of parallelism, these two instructions, if they try to execute parallelly, in that case your second instruction subtraction trying to read the value of R1 before your first instruction is going to write this result into your R1. So what happens here? After this execution only it can write, but before write that result into R1, if subtraction 2 is reading your R1, then subtraction 2 will get the old value, right? Not the new value. Okay, so that will execute incorrectly. That gives the output of your program incorrectly, right? So the hazard is this hazard is the most common type and corresponds to a true data dependency. The value of this is a true data dependency. So program order must be preserved to ensure that your subtraction instruction receives the value from your addition instruction. So this we call your read after write. If before write, if your second instruction reads, that gives the what you call the incorrect value. Okay, am I clear? Are you getting this? Read after write. Okay, that's good. Okay, yeah, right. So next comes to the second hazard is, yeah, thank you, Alvin. The second one is your write after write. So again, consider suppose we have instruction I and your instruction J of your program, which are two instructions in this. So write after write means if your instruction J, it tries to write, if instruction J tries to write an operand before it is write by your I instruction, suppose. So in this order, in the program, it says that first write the by your I, then write by your J. That's a condition. Okay, but J tries to write an operand before it is written by your I. So the writes end up being performed in the wrong order. So leaving the value written by I rather than the value written by J. in the register or memory destination, right? So this hazard corresponds to an output dependency. This hazard, this write after write, is depends. This hazard is corresponds to your output dependency. So in this order, first I must write and then J must write. But before I write, if J writes, suppose, and after that I writes, then that value remain in the register file or your memory. So next, if any instruction is there, suppose instruction K is there, the K is supposed to get the value which is written by your J, but because of the write after write means before written by your I, J is written, so then your I is written, so your instruction K get the wrong value because of this write operation. So this is another hazard, the write after write. So this write after write hazards are present only in pipelines that write in more than one pipe stage or allow an instruction to proceed even when a previous instruction is stalled. So that is your write after write hazard. Next one is your write, sorry, this is not right after it is right after write is your output dependency. And next one is your write after read. Right after read, that means again you just consider there is a program having the instruction I and your instruction J. Okay, so then J tries to write. J tries to write a destination register, suppose your R1 register, let us assume, tries to write a destination register before it is read by, before it is read by your instruction I, before it is read by the instruction I. In this order, I is first and then your J instruction in the order, but J is writing to your register, destination register, before your instruction I is going to read that register. That means what happens here, your I gets the new value, not old value, but actually your instruction I needs the old value, but gets the new value. Again, it gives a wrong output for a given program. Wrong output for a given program. Yeah. There is a question, Malino, right after write. Yeah, sorry. Right after write is an output dependency. Read after write is your true dependency. Am I clear here? Okay. Yeah. So then we are talking about the, so this is what, if J writes first in the destination where your instruction is, I is trying to read that, but in that case, again, there will be a wrong data here. So this right after read hazards cannot, this hazard arises from an anti-dependency. This, the right after read, this arises the anti-dependency, because both the instructions are using the same named what you call the register, one for reading purpose, one for your writing purpose. So your read after write is your true data dependency, where your write after read is your anti-dependency. Write after write is your output, sorry, your output dependency. Output dependencies. So in this read after write hazard, this var hazard cannot occur in most static issue pipelines, even deeper pipelines or floating point pipelines, because all read are early in instruction decoding in the pipeline, and all writes are late in the write back stage. So because all the it is generally not happens. Why? Because in the instruction decoding only, all the register files, registers will be read, and when the instruction reach to a write back stage, then the write operation, write to your register file will be there. In instruction decoding, the read operation will happen here. Okay, so the most complicated one is your true data dependent one. We'll try to look into this in details in the true data dependency one. Okay. Now, we'll see with an example here, the read after write hazard. So we have we have four instructions: instruction 1, instruction 2, instruction 3, and instruction 4. So all the instructions are having the same class of operation, that is add operation, and having the register variable, the operands here. Now clearly see here the instruction 1 is add R2, R1, and result will be stored into your R3. And in the second instruction states that add R3 and R5 and store the result in R4. Third instruction, add R3 and R5 and the result will store into R6. Fourth instruction, R3 and R5 result will store into your R7. So from here, let me just write this instructions. I'll just use this space. Okay. So here you can see the first instruction for your doing the read after write. To check it out, we have four instructions. The first instruction is your instruction 1 is add R3, R2, and R1. Instruction 2 is also add your R4, R3, and R5. Instruction 3 is also add, okay, your R7 with R3 and R6. Instruction 4 is add your R9, your R3, and R8, suppose. Now tell me, is there any data dependencies in these instructions? Is there any data dependency in this instruction? Yeah. It is clearly, yeah, you can see clearly here, instruction 2, instruction 3, and instruction 4, these three instructions are depending upon the result of your instruction 1. Result of your instruction 1, right? So out of 4 instructions, the next ordered instruction 2, 3, and 4, they are depending upon your instruction 1. Why? Because instruction 2 is required this first source operand R3, that is depends upon the result of your R1. Instruction 3 is also having R3, that depends upon the result of your R1. I mean the instruction 1. Fourth instruction is also having R3, that will again depends upon the result of your instruction 1. So there is a dependency here. Am I clear here? Good. Okay. So now let us try to execute these instructions. Let us try to execute this instruction. So let us go with the cycle 1 in the first cycle. In the first cycle, first instruction will be entered into your instruction fetching and use the instruction memory to fetch this instruction, because all these instructions will store in the instruction memory in the first cycle, right? So the program counter, instruction memory, and your adder are busy with your instruction 1, right? So the second instruction cannot get into the pipeline. When in the second cycle, okay, in the second cycle, this instruction 1 get into your instruction decoding, okay? So there you find the first instruction entered into your second cycle, that is instruction decoding. In this instruction decoding, you can see this, the first half is used for the write purpose, second half will be used for your reading purpose, okay? Whereas your instruction fetching, there is no structural hazard problem, so that will be continue as it is. Now, when in the second cycle, when your first instruction entered into your instruction decoding, your instruction fetching will be free. So instruction fetching will, those functional units will assign to your second instruction, that is instruction fetching with your memory. Let me just write instruction fetching only for simplicity, okay? Now, in the third cycle, your instruction world will get into the execution mode. So that means it use the arithmetic and logic unit, correct? And your instruction 2 will get into the second stage. Why? Because your instruction decoding will become free here. So it will enter into the second part of the instruction decoding will be used by your second instruction. So instruction fetching will be free, those functional units. So that will assign to, the instruction fetching will assign to your next instruction, third instruction, that is your instruction fetching stage, okay, using the instruction memory, correct? So in the pipe, there are 3 instructions. In this pipe, there are 3 instructions at cycle 3. These 3 instructions are not using the same hardware component, so no problem. So at the fourth cycle, your instruction will be, the first instruction entered into which stage? Your fourth instruction good. It enters into your memory stage. Very good, super. Now tell me here. It will enter into the memory stage, and your second instruction try to enter into your execution stage, right? As usual. But now you tell me your second instruction needs the instruction decoding here, right? Okay. In the instruction decoding stage, your instruction 2 needs the value of your register R3. The value of your register R3. Is that value is readily available for your instruction 2 here at this stage? Because instruction 1 is still calculating, your instruction 1 is still computing in the third cycle. Instruction 1 is still computing R2 plus R1, not yet executed. But at the third cycle, your instruction 2 needs the value of your, at this stage, your instruction 2 needs the value of your R1. It requires, it requires the R3 value. Is that R3 value is still available here for this instruction? Let me just write this. Now tell me, yeah. So at this stage, at third cycle, your instruction 1 is in the execution mode. So still it is computing, R1 plus R2, but not assigned to your, the R3 here. So, but for during the instruction decoding, your instruction 2 needs R3, that is not yet available. So this we call, there is a hazard. There is a hazard, because if your instruction 2 reads R3 value, that gives the old value. That gives the old value, not new value. Am I correct? Are you following this? Good, good. This is very important because, in assignment and exam, you will get around 30 points on this. If you are confused, please feel free to ask, okay? Yeah. So now at this stage, there is a complex problem here that the data is not updated. So in the fourth stage, let me just quickly go and write it, and then we'll try to find the result. Okay. So here, if your instruction 2 tries to read, it will give the old value. It will give the old value for, okay. Another one is, let me continue this, okay. Now, so there is the problem, I think you understand. Now, at this fourth cycle, instruction 2, assume that entered into your execution mode, and instruction 3 will enter into your instruction decode mode. So your instruction 3 will be entered into your instruction decode mode. Okay, then your instruction fetching functional unit become free. So that will assign to your next instruction, that is your fourth instruction. So instruction fetching will be done by your fourth one. So in the fifth cycle, your instruction 1 will enter into your write back stage. Entered into your write back stage. Then your memory access stage become free. So that will be assigned to your second instruction. That is instruction will enter into your memory access stage. And your instruction 3 will be entered into your next stage. But before here, you can see this. So we have seen what is the problem with instruction 2 at cycle 3. Now at cycle 4, you can see your instruction is, your third instruction is at cycle 4, read the register file. In that, your instruction 3 also requires R3. But by this time, your result is not right back into your register, correct? It is still in the memory segment. So do this instruction 3 will get the register value, the R3 register value here, the R3 and R3. So your instruction, why is there a gap between instruction fetching and decoding for every instruction? The gap between decoding, as we said, to solve the structural hazard, we follow the cycle timing, the second solution for structural hazard. To overcome from the structural hazard, we say the first half cycle used for writing purpose, second half cycle is for reading purpose. We talk more about this. Okay, so now in instruction fetching at the fourth cycle, instruction 3 needs the R3 value, which is not yet written back by your instruction 1, because instruction 1 is still in memory access stage only, not in the write back stage. In the write back stage only, it is going to write the result into your register file. Correct? So now here, still in this case, it's instruction cycle 3 and cycle 4, instruction 1 and your instruction 1 as well as and your instruction 3, if they try to execute, suppose without following, they will get the wrong value. The wrong value in register R3. So that wrong value means they will get the old value, not the new value which is computed by your instruction 1. Right? And suppose if it is start writing, okay, so then your instruction 3 will enter into the next stage, that is your instruction decoding. From here it will enter into your execution mode. Then instruction decoding functional units will become free, so that will assign to your fourth instruction. In the fourth instruction, the instruction decoding will be there, right? So here also you can see at the fourth instruction, in the fifth cycle, your instruction 1 is writing back into your instruction 1 is write back into the register. Let me just erase this. Yeah. Okay. Yeah. As you said, in the cycle, in one cycle, the first part is used for your writing purpose, first half, and second half is used for your read purpose, read and write in one cycle. Okay. So now at the fifth stage, the first instruction will write back the result into your register file, and your fourth instruction try to read that R3 value, okay, which is already written in the first half cycle of your the first instruction. So your fourth instruction will execute without any problems. So that means here okay. So by this, the first half time, your R3 is updated with the new value. So in the second half cycle, your instruction 4 is reading this value. So read this instruction 4 read the correct value. Instruction 4 read the correct value. Okay. So in that case, so this is the case where it is happening in read after write. The solution for this, So this is the problem that it will find, right? So what you are getting here, from here, it is clear that this instruction one, your instruction one writes this R3, write the value R3 in the, what you call, in the cycle 5, the cycle 5, right? So then if you start, if you try to complete the execution of this uh, process in the sixth cycle, your instruction 2 will complete the execution. That is, in the first half, it will write back. In the first half cycle, it will write back. Your third instruction will enter into your memory access stage, the memory access stage, okay? And your fourth instruction enters into your execution stage. So in the seventh cycle, your third instruction will complete the write back stage, the first half, and your fourth instruction enters into your memory access stage. So memory functional units will be used. And in the eighth cycle, your the fourth instruction will complete its execution by write back stage. So all these four instructions will be complete their execution in 8 cycles. They complete their execution in 8 cycles. But in that, the problem that finding that if instruction 2 and 3 try to, without a halting, try to execute these, they will get the old value. That is, instruction 2 needs R3 in cycle 3. Instruction 3 needs R3 value in cycle 4. And in the instruction 4, reads the R3 at the second half of your cycle, so get the correct value only. So therefore, there is no data hazard for your cycle 4, but there is a data hazard for your instruction 2 and instruction 3 in this execution of this sequence of your instructions in the program. So am I clear how the data is depending here? Dependency, the data value. It is true data value dependent hazardity, right? Yeah, so now we detected there is a data hazard now, true data hazard now. Okay, now we need to find a solution for this. What is the solution for this data hazard? Okay, so the solution for this data hazard is, it requires the bubble form. Means one of the solution we say, for this read after write data hazard, one of the solution is stall the pipeline. So, but as we said, when this data hazards occurs, so before solving this read after write hazard, pipeline needs to be able to identify the data dependency that caused by this read after write operation, So the hardware component, the separate hardware component, uh, the hardware separate hardware component for detecting this data hazard. This data hazard is called we call that as your interlock, as we discussed, interlock, to detect this. So this read after write hazard needs to keep a register ID. This interlock needs to keep a register ID along with the pipeline stage. The pipeline stage. That means what? Here it needs to keep the register ID, that is R3, and what is the pipeline stage 3, R3 pipeline stage 4 for the instruction 3, like that. Okay, so that the interlock component, the separate component, that will keep this track and use that comparators to check for the hazards, Okay, so this is what the data hazard, how the data hazard happens, and what are the type of data hazards. In that, what is the first type? Read after write. Okay, so this instruction 2 and instruction 3, they must read the data after writing the data into R3. Instead of that, if they try to read instruction 2 and instruction 3, if they try to read the data before writing that into the R3 register by your instruction 1, then it leads to your read after write data hazard. So in that case, one solution is we need to stop executing these instructions. Stop executing these instructions until get the data right by your instruction 1 into this R3 register. We call that as the first solution. We call the stall the pipeline, and then that is stopping the execution process. So that means what? When instruction 2 is in the third cycle, waiting for the value of your R3, which is not available, then instruction 2 will stop. So this stalling will be done by your bubbling. So when this instruction will get means, after the fifth cycle, instruction 2 will get the updated value of your R3. So after getting this R3 value, then only your instruction 2 start executing in the sixth cycle. Then your instruction 3 also wait to get this R3 value up to your fifth cycle. When instruction 2 is already holding this instruction fetching functional unit, so instruction 4 cannot be entered into pipeline. So instruction 4 also stalled until the fifth cycle. So in the sixth cycle, instruction 2 enter into execution, instruction 3 enter into decoding, and then instruction 4 start getting the instruction fetching functional unit, and from there it start smoothly executing of instruction. So to execute these 4 instructions with this stall this pipeline, it will complete in 10 cycles. So because of that read after write problem, the number of cycles, because of that hazard, the number of cycles in the pipeline will be increased, right? So this is one of the solution. The remaining solutions we'll try to discuss in the next class. I hope you got understanding of this. Will there be any assignment posted soon? Yeah, as soon as we complete these hazards, we'll post the assignment 3. So that means probably in the end of your November first week, we'll post the assignment 3. Yeah, thanks, Sarat. Thank you all. That's all from my side. Yeah.